So we have a problem here that says that we have two graphs with two potential energy curves representing an object experiencing some sort of gravitational potential energy. And part A of this problem says, considering the total energy lines, the E total lines in each graph, we have to draw kinetic energy curves that correspond with the given potential energy curves. So obviously these total energy lines are going to be the deciding factor in where our kinetic energy curves end up on our graphs. So the first thing we have to do is we have to remember that in any energy situation, the total energy of a system is equal to its kinetic energy plus its potential energy. And when we have gravitational potential energy, this U here, our potential energy, is always going to be negative. And in any situation, our kinetic energy will always be positive. So depending on whether or not our total energy is negative or positive throughout the entire duration, that will decide where our kinetic energy curve goes. So let's use that to evaluate this first graph, this graph on the left here. We have a negative total energy. So our E total, which is negative, is going to equal our positive kinetic energy plus our negative potential energy. So as we said before, in any situation where energy is involved, our kinetic energy must always be positive. It can only ever be equal to 0 or positive from there. So at the point where we have a negative total energy and we have this curve that hits the total energy, the potential energy reaches the amount of total energy there is, and then gets less magnitudinally than the total energy, then our kinetic energy would have to go to be a negative value in order to compensate for that potential energy loss. So let's say that our total energy is equal to negative 15 joules. So if this is negative 15, and at this point up here, our potential energy reaches something like negative 5 joules, then our kinetic energy would obviously have to equal negative 10 in order to compensate for that. But that can't be because our kinetic energy can never be negative. So when we evaluate graphs like this, if the potential energy ever breaches the total energy curve when it's in the negative part of this axis, then this is the point where our kinetic energy must hit 0 in terms of magnitudinal energy. So our curve would look something like this, matching with our potential energy reaching this total energy, and the moment where this potential energy is equal to the total energy, our kinetic energy must equal 0. And from then on, it never goes past the axis. It stays at 0 as long as this potential energy remains above the total energy. So that is the first kinetic energy curve for this left graph. And now we just want to draw a kinetic energy curve for this graph over here, for the graph where we have a positive total energy. So this one isn't as big of a problem as this graph over here. because if we have a total energy that is positive equal to an always positive kinetic energy plus a negative potential energy, when we get to the point where potential energy is its greatest or the least negative, then it still hasn't breached the total energy because our total energy is now above zero. It is a positive value. So our kinetic energy will pretty much just correspond with the potential energy. So when the potential energy becomes closer and closer to zero, then our kinetic energy will come closer and closer to the total energy. So then we can just say that if our total energy is equal to 15 joules, and then our highest point of potential energy is still -5 joules, -5, then at this point where the matching kinetic energy curve hits closest to the total energy line, it will be equal to 20 joules. So wherever 20 joules ends up on this graph, which is just 5 units above the total energy. So about here. And with that, we can draw the corresponding kinetic energy curve matching with the potential energy curve.